Dr. Smagler, we are having a small inaugural session right now. So we are directly going to the session.
Yep.
Jairam, we can start the inaugural session so that others will join by that time. Okay.
Okay. Thank you. Okay, very good morning to all of you. We, the IIC cell of MES Ponnani College, is very glad to see you all here. So this is the launching of IIC activities for the year 2020 to 21 to 22 actually. And we are starting this IIC activities of MES Ponnani College with an impact lecture series. And fortunately, we are having one of the most eminent scientists in the field of solar energy and non-conventional energy sources, Dr. Smagel Karsano. So he will be delivering the impact lecture today on the topic emerging solar cells, design, application, and challenges. I have been associating with him for a long time. I know him from last 10 years, and we had published around 10 articles together in various journals. I welcome Dr. Smagel Karsano to the session, and thank you very much for accepting our invitation. And we are having the special guest today, Dr. Faisal Ghafoor, who is the president of deliver his inaugural message, and Dr. Ajim P. Muhammad, the principal of MES Ponnani College and the president of IIC. His motivations, guidelines is made the event. So he's going to make the event so effective, I think. And I welcome you, sir. And I welcome all the participants, faculties, students to the session. Thank you very much. Ajim, sir, please.
Thank you, Dr. Jairam. Respected chief guest of the day, Dr. Smagel Karsano, the resource person of this impact lecture series, which is organized under the innovation cell of MES Ponnani College. Dr. P.A. Faisal Ghafoor, sir, president of MES Kerala, Dr. Jairam, Dr. Selima, all other participants who are attending this webinar, and all my dear students. Today, we are going to attend the first webinar, which is organized by the Innovation Council of MES Ponnani College, because the Innovation Council of MES Ponnani College is just started. The Innovation Council is actually it's an initiative of Ministry of Education, Government of India, to develop a culture among the youth for promoting innovative culture, inspire and nurture young students by supporting them to work with new ideas and transform them into prototypes while they are in formative years. And as a part of this Innovation Council, so many other programs are also organized by the Ministry of Education. They are Innovation Ranking, Hackathon, IIC-THE 2.0. Young India, the full form of IIC-THE is Young India Combating COVID with Knowledge, Technology and Innovation. Another program is NISP, National Innovation and Startup Policy. Then another program is Kalam program for IP literacy and awareness. So all these cells are registered at MES Ponnani College this year, and as a part of this cells, each and every cells, we are simultaneously arranging programs in the days to come. So I am very much happy to welcome our resource person, Dr. Smagel Karsano, for being the resource person of this webinar, and Dr. Faisal Ghafoor, who is going to inaugurate this program, because nowadays NAC and other accreditation agencies are much concerned about this type of innovative activities, just like startups, innovation, incubation, research activities, intellectual property rights. And along with this Innovation Council, we are also planning to start an academic chair in the college, which is mainly focused upon research, innovation and technology. And one more cell that is called intellectual property rights cell, IPR cell, is going to start at MES Ponnani College within 1 or 2 weeks time. So I really congratulate the members of Innovation Council, especially Dr. Jairam and Ms. Salima, for arranging this webinar by this international webinar by inviting resource persons like Dr. Smagul for this program. And I really express my sincere gratitude to Dr. Smagul and Dr. Faisal Ghafusa for attending this webinar, and wish you all the success. Thank you very much.
Sir, Faisal sir.
Oh.
Mic to you. Mic to you.
Sir, just rotate your camera. Faisal sir, just rotate your camera. Yes, once more, sir.
Once more. ഇന്നും കൂടെ
ഒന്നുകൂടി ചെയ്താൽ മതി. Yes, now it's okay.
ശരിയൊക്കെ തന്നെയാണ്. പക്ഷേ അതിന്റെ പ്രോബ്ലം എന്താന്ന് വെച്ചാൽ അവിടെ ഇതുണ്ട്, അവിടെയാണ് അതിന്റെ മൈക്കിന്റെ കിടക്കുന്നത്. സാറല്ല, ഇപ്പൊ ഓക്കെ, ശരി, ഓക്കെ അല്ലേ?
ഓക്കെ, താങ്ക് യു. ഓക്കെ സാർ, ഓക്കെ,
വീണു മൈക്ക് കിടക്കുന്ന അവിടെ.
ഓക്കെ.
Sir, your mic is
precarious. മൈക്ക് അതിന്റെ അടിയിൽ പെട്ടിരിക്കുകയാണ്, അവിടെയാണ് പഠിക്കുന്ന മൈക്ക്. ശരി, നോക്കാം നമുക്ക്. ശരി. Respected Professor Smagul, Dr. Ajims, Dr. Jairam, and the fraternity of the Physics Department of MES MES Ponnani College. Today is an entirely different day for me because today we are discussing science. It is not usually well discussed in Kerala, even though we are supposed to be scientific people. As a matter of fact, there's a lot as far as Kerala is concerned regarding this discussion for which we have to learn from. As we know, Professor Smagul is from Norway, which is called the land of the midnight sun. However, what I have understood is that as you go away from the equator, it becomes more and more difficult for us to harness solar energy. So he is coming from a land where it is a bit difficult to harness, and we are from a place where it is easy to harness the energy. As far as the solar energy is concerned, or the alternate sources of energy are concerned, after the global oil crisis in the 70s and 80s, we are very much worried by it, especially because of two factors. One is the cost factor. Today, the price of petrol is more than a matter of concern, but for us it's a big matter of concern. As far as, because as the prices of petrol increase, then the cost of essential. So hence humanity has been searching in the geothermic energy, or whether it is the hydroelectric energy. We have found that the best source of energy would be the solar energy. And Kerala has got another problem. I'm just briefing Professor Smagul about this problem. Kerala has got the highest density of population in maybe still I'll call it the highest density of population. It would be around 870 or 900 per square kilometer. That means 900 people are living a square kilometer in Kerala, while probably in Norway, hardly 15 to 20 people would be living in a square kilometer of area. So that is a big difference. So what is the importance of that? The importance is that because of the carbon monoxide emission of Kerala also has got the highest number of vehicles on the road, including cars, lorries, trucks, buses, etc. And the carbon monoxide emission already has started producing devastating effects on the ecosystem in Kerala. So Kerala naturally should be more interested in these alternate sources of energy. And that is where the importance of an eminent personality like Professor Smagul comes in, because he is here to brief us on the photovoltaic cell, I think. or whatever you call it, the solar energy system, which Kerala has been trying to implement for a long time. We have been trying to implement the solar system over here because of these factors. One, the high cost of petrol. Second, the high density of population. Third, the problem of carbon monoxide emission, the greenhouse effect, and with the global warming phenomena. All of these, for example, we have had tsunami, we have had floods and all. I don't know how we connect it to all these things, but it is, in some way, it is connected. So these are the major things which are affecting us, and we are looking at all these things from that perspective. That is where we would like to hear a lot from Professor Smagul about this. Kerala is one of the states which produces maximum hydroelectric energy, because we have got nearly 20 rivers over here, and we have got a number of dams, and they are producing hydroelectric energy. But the use of electricity also is very high, because most of the old wood or charcoal or anything for this thing as a source of energy, and we are going in for petrol, diesel, etc. Now, coming back to the practical aspect of this, of course, in my house, I have got a solar energy panel installed, but it's only a house. But in our medical college, the total medical college is around 12 lakh square feet, and the terrace area would be around 4 lakh square feet. And we have been going in for a lot of discussions. We have been going in for a lot of consultations. We have been trying to come to an agreement with many of these solar companies. And unfortunately, Professor Smagul may not be knowing this fact that the solar is a bad name now in the state of Kerala because of the problem of some sort of a corruption involved in the solar affair during the previous government. Because we have got private companies also in, and we have got the government of Kerala has also come in with a scheme. For example, the government of Kerala has come in with a scheme which says that the government will provide the panels, and we have to give the electricity back to the government at a very low rate. Let us say at around here the normal rate of electricity may be between 7 to 10 rupees per unit, but we have to supply it back to the government at 5.6 rupees per unit. So the government is also very active in this, of how to make this a cost-effective scheme, and that sort of activities are going on, and many of the households over Kerala are having solar panels, and we are also heading for that. Actually, we were about to sign an agreement, because this solar panel in the MES Medical College would be one of the biggest solar panels, because projects in Kerala. Because we have got 1.2 million, I'm converting it to for your convenience, 1.2 million square feet of buildings in one campus here. And the production, of course, I am not an expert in telling you about how many kilowatts can be produced and all, but the productions are supposed to be quite high, far more than what our requirement will be. And that would be one of the major schemes which is going on. And so I think I have spoken enough. I just given an introduction to the subject, and we are going, and the aim probably is that now we have got solar panel cars coming in. We already have got electric cars over here. We have got hybrid cars over here in Kerala, of course, produced by the major manufacturers outside like Toyota and all. But we are trying to get a purely solar-driven car over here. So that sort of activity is going on, and as you know, even in America, I think the name of the car was Alpetra or something like that, which means broken wings or something like that in Greece. And they have produced a car now, but the cost of that car would be around 20 lakh rupees or something like that. So that activity, see, the problem here regarding these cars are that the car cost is too much. So that a recovery may not be possible in the number of years in which the car is in use. So in various areas we are trying for it, and main thing is using it for warming up, for producing electricity, for producing heating up water. All those things we are using, heating up our households. So all those things are being done here, and we would like to hear from Professor Smagul about what is the state of what. And of course, mine is a broad introduction to the topic, but this will be more of a scientific one, which would be of use to the physics students over here and all over Kerala who are listening into this. Thank you very much, Professor Smagul, for attending this meeting. Thank you.
Thank you, Dr. Ghafoor. So should I start the lecture, Jairam?
Yes. Sure. Yes. Thank you, Dr. Faisal Ghafoor. Thank you, Smaggle. I just want to give an introduction to you, Smaggle.
Yeah. Okay.
To the listener. Okay. Thank you, Dr. Faisal Ghafoor. Thank you, Dr. Smaggle. So we are about to start our lecture on the topic emerging solar cell design, application, and challenges. So we are having Dr. Smaggle Karzano here. He is one of the expert in solar energy and non-conventional energy research, and he got enough experience, more than 20 years experience in the field of solar energy research, and he has published 46 articles in highly reputed journals with an H-index of 26 and an ITN index of 71. He has over 6 patents with his name, and he's a research professor and a visiting professor in many universities. He is an expert of GYAN, organized by MHRD, Government of India, and he is the reviewer of many journals in Elsevier and Springer, as well as he is the reviewer of Australian Research Council and Estonian Research Council, and chairman and co-chairman of various scientific bodies. So I welcome Smaggle to the session. The mic is all yours, Smaggle. You can start.
Thank you.
Please.
Do you see my screen?
Please.
Yeah. Do you see my screen?
No, sir.
Okay, good.
We are not able to see the screen.
Do you see now?
Not yet.
Okay. Yes. So it's a great pleasure to me to deliver this lecture to you and to participate in the event. I'm very thankful to organizers of the event, to Dr. Jairam, and for inviting me. And I have close cooperation with Dr. Jairam since 2010. And we have published many articles on the materials science. And we are keeping still then very good contact. And recently we have accepted one PhD student recommended by Dr. Jairam. And she will start PhD, which will be jointly between Madurai Kamaraja University and our institute. It is the topic will be related to solar energy. And today's lecture is about emerging solar cells, design, applications, and challenges. In the market, there are, you can find many types. Hello?
Sorry for interfering. Smaggle, sorry for interfering. Your screen is not visible, and please switch on your camera also.
Okay. So let me then.
Your screen is not visible too. Not visible.
Yes. Do you see now?
No, your screen is not shared.
Okay.
You can go to presentation. Yes. Now it is coming.
Okay,
yes,
good. Yes.
Yes.
So now then I will go. Yeah.
Can you go to the full screen?
Yes. Now I will do that. Yes.
Thank you very much.
Is it okay now?
Yeah.
Good. So in the market, one can find there are many types of the solar cells and solar modules. And among them, it's good to find which one is best, which one suits to the local climate conditions. Now, as you know, there are 4 generations of solar cells, and the work is ongoing about 5th generation of solar cells, and also, however, each of them, and in each generation, there are so many varieties of solar cells. So what is good is for public to know, to users to know which one is best, which one suits to our purposes best. And also, then when this type of products are distributed in the market, it's good if local experts will take care of quality of this product. As you know, there are now in the market many products, like, for example, gene-modified products, and some of them contain very detrimental chemicals. And however, the companies producing such foods, for example, with gene-modified incorporations, they notify the buyers, the users, but they will indicate only numbers, which is called PLU code. And if the PLU code number, the first number is 4, and if it's more than 4,000, then it means it's it's not healthy. And it contains some elements which are detrimental to human body. However, those who are selling, they need somehow to get the money back that they have spent for the research related to synthesis of the genes, and then the synthesis and characterization of the gene-modified foods. The same can be applied to solar cells. There are, if each generation solar cells contain many types of the solar designs, then it's good to know which of them is best. So then today I would say briefly about the 4 generations of the solar cells, and then for the photovoltaic modules and artificial photosynthesis. In case of the artificial photosynthesis, and one can use here solar cells as well. So I will tell it briefly afterwards. So as to photovoltaic technology, and it is the technology that allows us to convert solar energy into electrical energy. The good part is that the energy coming from the sun, it's enough to satisfy the human demand in energy. The only thing is that the energy is distributed, and we have to collect them somehow. And then we need these devices, photovoltaic devices, to be installed on large area and to harvest this energy. Then these devices should be efficient. So efficient, I mean here, efficiency should be high, so that they should convert as much part of the solar energy as possible. And then they should be operating within at least 20-25 years. Then it will be useful. However, when real applications have been started, solar installations started, then some challenges have been found. So then it means that we should take into account the influence of the environment. And those things I would like to address in today's lecture. So then the first generation of solar cells, they are made of silicon. And the first generation cells are taking about 92% of the photovoltaic technologies in the market. And the rest 8% is coming from other types of solar cells. So I would like to devote most of the part of today's lecture to first generation solar cells. As to the rest, thin film solar cell technologies and emerging concepts, it's clear. Until they will come into the market, it will take a lot of time. So the first generation solar cells, they are high cost, and they are made of silicon, and it can be crystalline silicon, it can be polycrystalline and the multicrystalline silicon. But the best ones are made of single crystalline silicon, and namely a float zone silicon. And of course, even with the first generation cells, there are a lot of work ongoing by implementing plasmonic effect, by hybrid cell concept, and so forth. Second generation solar cells, they are made of thin films of solar cells. If the first generation cells are very thick, their thickness is about 250 micrometer. Now, in the world market, a struggle is ongoing about reducing the wafer thickness up to 180 micrometer. So probably nowadays they will use 180 micrometer wafers. Why 180 micrometer? Why not 1 micrometer or nanometers? It is, related to electronic structure of silicon. Silicon's band structure, it is indirect, and then its light absorbing capability is poor. So to harvest the sunlight efficiently, one needs thick silicon. And 180 micrometer to 250 micrometer cells, 250 micrometer would absorb sunlight efficiently, whereas 180 micrometer cells, they will also absorb efficiently, but not as 250 micrometer. And why then we are using 180 micrometer? It's because there are defects inside silicon, and those defects will be as centers of recombination for charge carriers that have been generated by illumination, by sunlight. And to reduce influence of those defects, it's better to make thin films also, thin wafers also. And in the second generation solar cells, those materials are used that very efficiently absorb sunlight. And they are just a few micrometer thick and about 10 times thinner than silicon, more than 10 times, so maybe 20 times thinner than silicon. And they will absorb almost the same sunlight as silicon. And they are flexible, whereas silicon solar cells, they are not flexible. They are they can be just easily broken. And then I will tell about representatives of those cells also. And then a third generation solar cells came to the scene. They account for all advantages of previous two generations of the solar cells. So in the second generation, the method of fabrication of the cells is low cost, and efficiency is low also. In the first generation, efficiency is high, cost is high. In the third generation cells, it is expected that efficiency is high, the cost is low. However, third generation solar cells, it's just entering the market. And one example is perovskite solar cells and dye-sensitized solar cells. What type of deficiencies of the first generation cells have been accounted for in the third generation? So in particular, it's by using intermediate band solar cell concept, by using the energy of the hot charge carriers. For example, in silicon, band gap is 1.1 electron volt, whereas it can absorb high energy photons as well of around the 3 electron volt as well. So then how to use rest 2 electron volt, okay? Then that can be somehow utilized, that excess energy also. Then this hot carrier relaxation. And in the bulk material, the hot electrons of energy of 3 eV, the carriers will relax quickly to conduction band minimum, and then just releases that excess energy and that will be spent to heating of the lattice. And instead of heating the lattice and being not utilized properly, so there are some concepts that will allow to use that energy for efficiency enhancement of solar cells. And now fourth generation solar cells are available, and they include hybrid nanocrystal cells. So the inorganic and the organic materials will be combined, the hybrid materials. And this type of solar cells are also available today. Efficiency map has been developed by the National Renewable Energy Laboratories for both solar cells, different types of solar cells from different generations, and efficiency map for solar modules. So in this table, you can see efficiency map developed for different types of cells. On the left-hand side, you can see the list of the cells. And then on the table, it's written name of the company or institute who produced it. So solar cell, it is a device, it is a small size device produced in the laboratory scale. And they will be connected to each other and form modules. If we are considering silicon-based modules, then we can say the following. Silicon-based solar cell itself, its size is about 10 by 10 centimeters square, okay? And whereas in one module, there will be several solar cells. So the very common ones are 64 solar cell or 72 solar cells are involved into one module. And one module, its weight is about 15 kilogram. And the module's efficiency and the cell efficiency, they are different. Module efficiency is lower than cell efficiency. Cell efficiency, if it's about 25%, then module efficiency will be lower. And so this module efficiency table has also been developed by the National Renewable Energy Laboratory, and one can easily find these latest developments on these tables on the website of NREL. So then at the beginning of the lecture, I would like to say first about the first generation solar cells that are made of silicon. Principle of operations of the both first and second generations are based on p-n junction. P-n junction should be, for the material to develop, to bring photovoltaic and the photocurrent. Just one material itself, it absorbs sunlight, and that's all. And for the device to form photovoltaic, there should be p-n junction. The p-n junction's role is that sunlight generates free electrons and free holes in the material, and the p-n junction splits them. So the holes will be in p-type side, electrons will be on n-type side. As a result, we will have two different charge regions. When it's connected to each other, then electrical current will go through load. And so in this solar cell, which is on the left-hand side of the picture, one can see emitter layer, which is very thin commonly, and the electrical conductivity type N. And it means the base layer of the solar cell is possessing p-type electrical conductivity, so p-n junction. On top, there is a passivation layer or anti-reflection coating. In the subsequent slides, I will mention briefly about why we need passivation layer and why we need anti-reflection coating. But the material itself is multifunctional. It combines two properties. One is surface passivation property, and secondly, it is and the light reflection capability is good. And also, surface of silicon will be texturized. And as you see on the right-hand side of the picture, this is surface of texturized silicon. Some pyramids have been created. These pyramids are served to reduce light reflection from silicon surface. Silicon, when its surface is cleaned very well, it reflects about 36% of sunlight. Reduction of it's possible by using anti-reflection coating on the one hand, and on the other hand, by texturizing the surface. Surface texturization is possible by using some very detrimental chemicals like HF. Industry would like to avoid it, but this is not possible. So since silicon is occupying about 92% of the world market on photovoltaic technology, so once there is no other way, so then everybody agrees that HF will be used here, no other way. And front contact is used from silver and back contact is used from aluminum. And however, when aluminum is used, aluminum is metal. And then aluminum during processing screen printing of aluminum paste, some aluminum diffuses inside silicon. And then there will be very thin layer, and that is marked with green color, and that the aluminum heavily doped silicon forms back surface field, which contributes somehow positively. Now let's analyze the cell design. I mentioned about surface passivation layer, why it's needed. It's needed because the silicon surface is open, and there are some silicon atoms that doesn't have bonding with other atoms. And those dangling bonds will create intermediate and the centers of recombination. In addition to it, they will be reacting with the atoms of environment. And those create again the band gap states that will be as centers for recombination of charge carriers. So when we illuminate the silicon wafer, please see the picture on the left-hand side of the slide, and it will create free electrons holes, okay? And those free electrons holes, for example, here, the electrons in N++ region, they should reach somehow contact, metallic contact, silver. So then the more they live in the N+ region, the more is the probability that they will be reaching the metallic contact and diffusing it, and then it will contribute to electrical current. In case if the surface is not passivated, then majority of those charge carriers will just die at the interface. So one should passivate them well. And there are different materials groups that passivates very well, and but not all of them are suitable. Among them, the very suitable materials are silicon nitride that passivates very well, heavily doped silicon that possess N-type electrical conductivity. There is another successful material, which is aluminum oxide, and that passivates very well N-type electrical, P-type silicon. So yes, now we know that we need certainly passivation layer. And in the next slide, of course, I will say you why we need this anti-reflection coating also. And you see here metallic contacts from silver. And on the here you will see you see the schematic image of the solar cell. And these the very thick lines, they are called bus bars. And at the bottom figure you see image of the solar cell from top. Okay. The white lines, they are bus bars, and the very thin layers are fingers. And this is picture of the like a 3 busbar solar cell. In fact, number of busbars nowadays have been increased. 3 busbars, no company producer is doing producing now 3 busbar cells. And some time ago they were producing 5 busbar cells, but one can hardly find it now in the storage room. And now the majority of the producers, they are producing 9 busbar solar cells, and even more, multiple busbar solar cells, and as they are found to be more efficient. So then the point is here, okay, so then the question is how wide, how thick these busbars and fingers should be. And one should, for that, analyze how the solar cell efficiency will depend on these parameters. So let's analyze electrical resistivity of these metallic contacts. and it's proportional to resistivity times of the metal, and the length divided to width and height. So it means, as to length, we cannot control, we cannot reduce it less than the wafer size. So it's fixed parameter. And the little rho, this is also a specific resistance. We cannot change it also. So it's fixed. I mean, it's fixed, and how company produces what type of wafer, that one we will use. So we it's hard to influence on that. Then we can tune width and height. Okay. However, we can make it very wide so that it will cover the whole solar cell. However, that's not efficient. Then just solar cell, instead of absorbing sunlight, it will just reflect them. So then we should somehow select the optimal width and optimal height as well. So for that, one should analyze power loss as a function of the width of the bus bar and height, and then find this type of optimal optimal width and height. So then also I discussed the question about light absorption by silicon, and the light absorbing capability. It depends on absorption coefficient of the material, and absorption coefficient, its spectral distribution, it depends on electronic structure of the material. And since silicon is like indirect bandgap material, so then the light absorption occurs within about 180 to 150 micrometer scale. Yeah. So then let's now discuss why one needs anti-reflection coating. So as I said, when silicon surface is well treated, and when the surface states have been removed by HF treatment, silicon reflects more than 30% of the sunlight. Is it possible to reduce it? Yes, it's possible to reduce it. Just one should deposit on top of it a different material of certain refractive index. And a refractive index of that material should satisfy this following relationship. And this relationship has been found long time back by Sir Relay. And this is refractive index of the anti-reflection coating material. This is a refractive index of air that will be after this anti-reflection coating material, and a refractive index of the main material, which will be underneath the anti-reflection coating. If we are using silicon, then we should use silicon's anti-reflection coating, which is 3.4. Refractive index of air, which is above anti-reflective coating, it's 1. It means anti-reflection coating of this material, it should be about 1.85. If we analyze refractive index of silicon nitride, it's about 1.9. And that can be tuned as well by changing the nitrogen stoichiometry and by hydrogen doping also. So it means that this one is a very suitable material. Whereas refractive index of aluminum oxide that I mentioned already, it's about it's slightly above 1.5, so which is also close to 1.85. So then that's why these two materials are very popular, as they will passivate surface efficiently on the one hand. On the other hand, they reduce light reflection from silicon surface. Now let me discuss with you different types of silicon-based solar cells. There are now so many varieties. I will just list a few of them, okay? And one of them, on the left-hand side, you see the very standard silicon-based solar cell, the first examples, okay? It's made of p-type silicon wafer, and there is on top of it is very thin emitter layer, which is made from phosphorus doped silicon, and then passivated by silicon nitride with front aluminum contact. And then on the back contact, there is, aluminum. So then what stands for passivated emitter with rear locally diffused parallel cells? So here, first of all, the metallic contact, as you see, it's not continuous as it's here. it's locally diffused. These small spots will be opened by laser, and aluminum will be here. And then aluminum will be split from silicon with very thin metallic layer, oxide layer, sorry. And aluminum will diffuse just through these openings, laser openings. And then form here P+ junction, and the current will be collected in this way. And emitter is, of course, passivated again by silicon nitride. So this is the example of the Pearl cells. And the Pearl is developed by University of New South Wales, Australia. Then another example is PERC cells. This one is one of the very popular solar cells now, which is in the market. Efficiency of the cells is very high. And here, as you see, it's on this left right hand side picture. The top of the cell and the metallic contact is passivated also. So with the very thin oxide layer. So this is called the PERC cell, passivated contact. And then there is also one of the cells, it's called paired cell. This is totally diffused cell. And here this between the back contact and the base layer made of N-type silicon, there is back surface field. That back surface field is made of phosphorus doped silicon. It's but main p junction is here at the front side. It's made of by boron diffusion of boron diffusion silicon. But if boron diffused silicon, then one should use like aluminum oxide based passivation layer, and on top of it only silicon nitride, because efficient firing of metallic contact can be made by through silicon nitride. Yes, so this is example of the paired cells. And there is now TOPCon cells. TOPCon is now emerging solar design concept. It's made of, again, on silicon, and it utilizes N-type silicon wafers. And when it was first developed, it's developed by Fraunhofer Institute for Solar Energy Systems in Germany in 2013. So since then, it's now a very popular cell now. Efficiency is already like above 23%. So, and here it usually utilizes polycrystalline silicon, and that polycrystalline silicon is isolated from the main base line by ultra thin silicon dioxide layer. And another very popular and emerging type of solar cell, it's called the heat cells. HEAT is acronym. It's on the heterojunction and the insulating layer solar cell. This was developed by Japanese company Sanyo in 1980s. And here, why it's heterojunction? Here, amorphous silicon is used that possesses different bandgap than crystalline silicon. So here it's heterojunction. Here, advantage of amorphous silicon is used on making p-n junction with silicon on the one hand. On the other hand, it can passivate surface well. And intrinsic thin layer is intrinsic amorphous silicon is used also. And so why it's called heterojunction with intrinsic thin layer. And this intrinsic thin layer is of thickness of about 20 nanometer. So then a hybrid solar cell concept is available now. It combines crystalline silicon with organic material. This solar cell concept came out because of complications provided by silicon by fabrication of emitter. Emitter is made, for example, if we have N-type silicon by diffusion of boron. But the boron doping with boron is commonly will be Because of high temperature process, the samples should be heated up at temperatures exceeding 900 degrees C. And in that temperature, silicon's property will be damaged. And then subsequently, after boron doping, one should clean the surface again, remove some surface layer by HF treatment, which is a time-consuming process and energy-consuming process also. Whereas nowadays, many types of polymers have been discovered that can be deposited on top of many substrates at the room temperature. So this was a concept about making a P-type polymer combined with N-type silicon. And efficiency of this type of cell already exceeded 20%. And now let's come to thin film solar cells, which are inorganic cells. So, and one of the examples is the thin film silicon-based solar cells. But this type of cell, it's not popular at all. It's because of durability. Durability is still less than maybe 5 years, depending on producer. And some of the producers produce maybe like modules, silicon-based, amorphous silicon-based modules with durability of 1 day maybe. So it's and some of them durable in the sense that it can be just 5 years. If durability will be longer, let's say 10 years, then it would come to the market also, of course. Cadmium telluride-based solar cell is available in the market, and the company First Solar is a leader of this company, of this type of the solar cell. And it's flexible, and it can be inkjet printed. But here there are some challenges. The challenge is related to availability of tellurium. Tellurium is one of the strategic elements in the Earth. And of course, cadmium is poison, but this poisoning property will be available only during material synthesis, probably. But during utilization, no, because for this poisoning property, cadmium should be released, but cadmium release will be at temperatures at exceeding 1000 degrees C, whereas these type of solar cells will be utilized in terrestrial conditions at room temperature. So poisonous of cadmium is not an issue. The issue is with availability of tellurium. Then the other candidate is CIGS solar cells, copper, indium, gallium, sulfide. It's heterogeneous solar cell quaternary compound. Its band gap can be tuned from 1.1 to 1.9. And its efficiency nowadays is above 20%, but as you see, it's 4 different compounds are there, and the elements are there. And it's very difficult to get pure material here. So there will be plenty of anti-side defects and chemical defects a lot. But this material still is very much interesting. Here, the challenges probably is about availability of indium. Indium is one of the strategic elements also. So this is the table of the area and the availability of some elements, and the tellurium and indium, they are in this region. So here it's indium. Availability of indium, it's in the some geographically limited area. Mostly it's coming from China. And then another interesting element, solar cell, it's CZTS, copper, zinc, tin, sulfide. And efficiency is too low for this type of cell. It's about 12.6% to today. Still, this is much lower than 32% predicted by theory. So the research is ongoing about this solar cell. And now classical element, the single elemental semiconductor, selenium. The first photovoltaic effect has photoelectrical properties of the material have been discovered for selenium, and since then, when people found the silicon and other 3-5 materials, semiconductors, they just forgot about selenium. And now, to today, selenium-based solar cells are very popular. And efficiency is, of course, still too low, but it is something. And people are getting interesting results from selenium-based solar cells. Design is very simple. And now another popular element from thin film solar cells, this is antimony selenite-based solar cells. And we are working now on this type of solar cell. And so we have at present one project about antimony selenite-based solar cells. Efficiency of the cells, it's now has reached about 10%, but there is big room still for scientific research to achieve better efficiency. And the main challenges with this material is synthesis, understanding the deposition and the synthesis conditions. And it will grow up with columnar structure, and this columnar structure, it should be perpendicularly located to the substrate, and it's very difficult to get it. So one should develop a good method for getting it, simple method. And the other reason, other challenge is controlling of electrical conductivity of this material. In case of silicon and the gallium arsenide, for example, people already know which impurities should be incorporated to get N-type or P-type and how to do it. In case of antimony selenide, it's not clear yet. Even it's not clear which type of impurities here gives N-type, P-type. According to theory, one can just say, okay, let's dope with 4 valent elements that will replace antimony, but that's not so easy. Because if one incorporates such impurities, then another defect can be formed during the doping process that will just passivate the defect. So this question is also another open question. And the third open question is interface. So this material can be very good light absorbing material. However, that charge generated, the electrons holes generated by illumination should be transferred to the neighboring layers, to metallic contact, and then to another layer. And here, interface should be good enough. And so this is a topic for scientific research at present. Now let's come back to solar modules. As I said, solar modules are made of solar cells. In case of like the thin film solar cell technologies, they can just initially put substrate. At the end, they can get the module also. And this type of technological chain can be developed for printing and for sputtering also, which is very simple. And the process of making module is not so trivial, and there are many plants. The company produces, they have very big plants that are producing solar modules, and this is just a different story. So how to make solar modules? Let's say we have a two silicon solar cells, okay? Then bus bar of one silicon solar cell should be connected to back contact of the next cell. So then it will be in series connection of the cells. And the cells can be connected to each other in parallel also. But then, of course, bus bars of two cells should be connected to each other and back contacts to each other. And by this way, one can get the necessary amount of voltage and electrical current. So in series connection, then of course current is constant, voltage is added. In case of parallel connection, voltage is constant, but the currents are added to each other. Okay. And so by this way, and in one solar cell, one module, there can be, say, 64 or 32, 24 or 72 solar cells. So most popular one is 72 solar cells. So then modules, these modules can be connected to each other in series or in parallel as well. Thus, output voltage, output current will be controlled. And the magnitude of the current and voltage, it will be depending on what the customer wants. So, and now we have seen how these solar cells should be connected to form a module. And inside the module, there will be frame and a protecting layer from glass. And then solar cell will be encapsulated from both sides by EVA layer. It's encapsulation layer, ethyl vinyl acetate. And then the system will be heated to I think 110, if I remember correctly, degrees C. Then it will be melted and connected to the solar cell. So why this protection by glass is needed, you see on the right-hand side. So in real utilization, they should be mechanically strong and that are very transparent to sunlight layer. And there have been several attempts to replace glass layer with something else, which will be lightweight. As I said, weight of one module is about 15 kilogram, and most part is coming to glass. So if one can be able to reduce weight of the glass to find the material that is at least as transparent to visible light as glass, and which will be lightweight and flexible, this is best case. So, and this is open question to today. And yeah, community is struggling to find the proper material. Then I said also about applications in realistic conditions, and these applications is creating big problems, and it's opening also a focus for scientific topics. One of them is light and elevated temperature-induced degradation of photovoltaic solar cells. So solar cells, for example, in Antarctic region, or in like India, for example, they are behaving differently. And the efficiency and the power generated by the solar modules at different temperatures, at 25 degrees C, at 55 degrees C, it's different. With even slight increase in the temperature from 25 to 55, the power generated by the cell will be different. Then it indicates that the cooling of the solar modules is an important challenge. Maybe this solar modules installed on Armada in India, Narmada, maybe it will be good, because then it will be cooled by underneath the water. And from underneath it will be cooled all the time with the water. But of course, it will influence on changing the flora and the fauna of the channel also. So. And not only efficiency, the temperature of the environment, but also illumination power also influences strongly. With increasing the illumination power, of course, efficiency is expected to increase. However, this efficiency increase, the enhancing light illumination enhances temperature increase also. So then, but temperature increase, as we have indicated, it will reduce the cell efficiency. It means that if we use in concentrator solar cells, silicon solar cells just will damage there. So it's, yes, and then one nowadays, these examples have led to starting different scientific topics. One of them is luminescent solar concentrators for building integrated photovoltaic effect. And the main concept here is that the material absorbs the whole spectra, I mean a wide spectrum of solar radiation, but it illuminates light in some specific wavelength region corresponding to the bandgap of the main light absorber. And by this way, it would be possible to reduce like heating of silicon, and it would open up the way toward using silicon in concentrator cells, for example. Here also another very interesting aspect has been used. One can notice for example, in deserts like Sahara, a lot of insects are living there. And also they are withstanding the high temperature in that region. And when the skin of those insects have been studied, then they found that they have been texturized very well. Okay. And then because of that specific texturization, irradiation of infrared light is enhanced. As a result, environment temperature can stay like 50 degrees C, 55 degrees C, but the temperature of the body of that insect is lower to 5 to 10 degrees C, which is significant. And such texturization schemes is under development for solar cells nowadays. So this is one of the popular topics now. And so the glass itself protecting the silicon modules when they are flat, they are transmitting about 92% of the sunlight only, which is too small. One needs to increase it up to 98 at least. So, and one of the ways how to do it is texturization of the glass. Nowadays, glass producing companies are selling modules texturized in specific way for the module producing companies. But this is again very dangerous case, because one should account for here I mean in the texturization influence of the environment. First of all, glass, it's amorphous material. How to texturize it? There will be no regular texturization like in silicon. And also, then one should use chemicals like HF, but if one uses then the texturization, it will not be regular. That's another issue. So this is another open question. Also, if one texturizes in micrometer scale to enhance radiation of heat waves, then in case of dust storms, if the solar modules are installed in Sahara, in Qatar, or in pre-Aral region and so forth, then these dust particles, they will just fill these texturized spots. And so here, then it means one should study the physics and the chemistry of dust in the region. If there are some salts coming out, then as you know, the salts will stack very well on top of glass. And then it will be very hard to remove them. And also, one more example that I wanted to show is birds are sitting there, because these solar cells modules will be installed a human unpopulated area, which is lovely place for birds. They will make a nestle there, and there will be bird droppings. And as you know, the bird droppings, if they will stay just 1 hour, then it will be like stone. It will be very hard to remove them. So materials are needed that are very transparent to sunlight. At the same time, it will be repellent to dust. Then that would reduce further reduce the cost, because you know, of course, human can clean it, or human, you know, but then each but for the human, one should pay salary. And this monthly salary, it will be added value to the cost of the PV energy. So in the laboratory scale, the price per watt can be too low, acceptable by the market. But if one accounts for how many maintenance costs will be added there, then it suddenly becomes problematic. Also, of course, one can use nanoparticles, okay, for that would be repelling dust as anti-dust coating, anti-soiling coating. But then it's very hard. This is on laboratory scale, on 100 nanometer scale. This type of closed packed particles can be developed. But can one do similar, just very close packed ones on large scale, industrial scale, for example, in 1 square meter? This is very hard to do it. If this type of small openings are available, that's more than enough. you know, and when this the dust storm will stay one day, that's more than enough. Just those would populate these openings, and then next day the module can be useless to use. So these are the challenges related to the solar modules. Dr. Jairam, how much time do I have now?
You can continue.
Okay, good. Just let me know when I'm, yes. And so now we are now aware about challenges about using the PV modules, okay? And today, there are different types of module designs are available also. So then one of them is half-cut monocells, okay? Shingle cells and multi-bus bars. Multi-bus bars, I told to you. And when number of bus bars are more than 9, that's multi-bus bar solar cells, okay? And the shingled solar cells, you have seen in many examples of the shingles on the roof of homes. It's especially in Norway. It's everywhere. So it's then half-cut module designs are available. Then the solar cells will be cut in half, and then that will reduce resistive losses and enhances efficiency of the cells. It was brought to the market by Norwegian company REC, it's Renewable Energy Corporation. That design has been introduced in 2014. So then, yes, multi-bus bar, I mentioned it already. Yes, so in the shingled panels, it's just one solar cell. It will be, yes, so the edges of the cells will be connected to each other in so nice way, like shingles on the roof. And that will give more efficiency. But of course, the work to be done is so complicated. It's not trivial work. And for that reason, price for the shingled solar modules is more expensive than half-cut modules. And now also bifacial modules are becoming very popular. And in the bifacial, so it will work on both sides. So in the previously mentioned solar designs, there was metallic contact, back contact. So now the design has been changed so that illumination can be done from backside as well. This is this type of bifacial modules would be very efficient for using, for example, in snowy regions, for example, in Norway. So there will be, on the one hand, the sunlight coming from the sun. On the other hand, diffused light reflected from the snow also. Then because of that, efficiency is expected to be like enhanced. So nowadays also, then as to applications, then building integrated photovoltaic technology is very popular. Road integrated PV is very popular, and here road design is used. Agriculture applications of PV is important. Transport integrated PV, and especially fish farm integrated photovoltaic technology, aircraft integrated photovoltaic technology. So then the applications of PV is becoming very, very important. So, and what challenges are there in, for example, building integrated PV? These are in the picture are examples of a city in Morocco, and in the living place in Greece, for example, Santorini. And as you see, it's this colors are identical in these two locations, whereas according to requirements of the market, and in some places they want mixed color, in some places like a black color, in some places red, green. So can we control color of the modules? Yes, so that's possible to do it. And for that, we will analyze the design, okay, of the solar cell. We have seen I have shown this picture already, where to change it. So one way is to change color of the glass, and the other way is to change color of the solar cell itself. And which one is better? In which case one would lose efficiency more. So such analysis has been performed, and then it's found that it's good to change color of the solar cell itself. That's possible to do it. And yes, this is a silicon solar cell. And I mentioned it about, I have shown this slide to you before for suppressing this light reflection from silicon surface. And by controlling thickness of this anti-reflection coating, one can control color of silicon also. So the best case, best efficiency is provided when color of silicon is blue. And this can be done at about 80-100 nanometer thickness of anti-reflection coating. If it is reduced to a little smaller value, then of course one can get green or pink. Different color is possible to get. Just then efficiency will be lower than blue color. But if we lose, for example, 2-3%, okay, but get different color, that's fine for market, because market is bringing money. So then we should fit, the criteria for the product should be not only efficiency, but also what what market wants. So yes, and the very exciting part is fish farm integrated photovoltaic technology. Different applications are possible here. For example, there are many regions which are located far away from human populated, from the water resources. Then pumping water, underground water can be done by using PV energy. Then this water collected into tanker, and they should be cleaned. For cleaning purposes, one should use energy. Again, here PV technology can be used. Then, for example, underground water, it will be oxygen deficient. Then enhancing oxygen level inside the water can again be done by using PV energy, not only PV, but also solar energy. And when it's used in fish farm, water quality will be worsened. And then cleaning of that water can again be done by using solar energy. So now integration of not only PV, but also the other types of the solar energy technologies like solar thermal collectors, photoelectrochemical solar cells, and the photocatalysis, for example, they are very important and very popular. And now in the European Union, a lot of projects and call for projects are available about fish farm integrated solar energy. So then this is example like autonomous mobile shop integrated PV technology, and like farmhouse integrated PV technology. This is example of roadmap, road integrated PV, and the vehicle integrated PV, and the flight integrated PV also. Yes, so as to challenges, I already mentioned it. On the wind energy, you might know a lot of interesting stories. So PV also is not very good in the sense that there are a lot of challenges related to applications of PV modules also that is creating a lot of problems. And one should account for influence of environment in the PV modules. So then I thank you for the PV related part of the lecture. And now the next part, it is about artificial photosynthesis. In the normal synthesis, CO2 is converted, this is CO2, it's a very harmful gas, but one can utilize it to convert it to fuel. For that, one needs hydrogen, but hydrogen one can get from photoelectrochemical solar cell. Photoelectrochemical solar cell is the device that splits water into hydrogen and oxygen. Then that hydrogen generated by a photoelectrochemical reactor can be spent for reaction with the CO2, and then the CO2 can be converted to fuel. The output products here can be methane, methanol, ethanol, and so yes, this is now very popular topic at present with technical readiness level between 1 and 3. Technical readiness level is the measure that indicates how far we are from basic research, how close we are to the market. The largest technical readiness level is 9. 9, it's after 9, its commercialization will be started. So yes, so this is the content of today's lecture, and thank you for your attention, and questions are welcome.
Thank you, Smaggle. Dr. Smaggle, thank you very much for the comprehensive and informative talk. Can you able to read the questions? We have some questions posted in the in-call messages. Can you able to see that?
Yes, now I see in the chat system.
Yes, Bhagavati has asked 2 questions. Can you read it?
Mm-hmm.
Which one is the best suitable material for? Oh, yeah, yes. Passivation layer.
So which one is the best suitable material for the passivation layer? Silicon nitride. Silicon nitride is the best material for passivation of heavily doped N-type silicon. And the aluminum oxide is the best for passivating P-type wafer. Silicon dioxide is okay, but it grows very slowly. And for its growth, one needs to heat the silicon to 900 or 1000 degrees C. Then it's possible to get, high quality silicon passivation by silicon dioxide. If one grows it and just in clean room within 24 hours, just 2 nanometer silicon dioxide can be obtained. If one wants to speed up the process and the heat, then the silicon dioxide will grow faster, but quality, passivation quality is not good enough here. So silicon organic solar cell complex, what is, yes, a very good question about stability. Today, PE dot doped with PSS has been used for organic silicon solar cell concept, but the durability of PE dot with PSS is too small, unfortunately. It's too short. And the hope here is that to develop the concept is available. And so one knows now that high efficiency can be obtained. Now next struggle is ongoing to enhance its efficiency to bring it up to say more than 15% at least. None of 15 years. So then what are the recent innovations in TPV, transparent photovoltaic technology modules? Yes. So there are a lot of innovations ongoing on TPV. So about getting transparent voltaic, and one of the latest developments is making and mounting these mini solar concentrators on the window also, so that to focus the sunlight on the next glaze and where solar cell is located. It's to harvest the efficiency of the sunlight, and using also low cost materials, half transparent materials, and the cadmium telluride has been used now, and the perovskite solar cells are used for transparent photovoltaic technologies. So then also, can we integrate thermochromicity with photovoltaics? It's another very good question. I don't know it, but I'm very much interested with that.
Yeah, that's a question from my side actually.
Oh, okay. Yes. How do the weather conditions affect?
Doing some work in thermochromicity.
Yes. And also Safna, how do the weather conditions affect the efficiency of specific photovoltaic module? Yes. And the dust is influencing quite a lot. Dust size, physical chemical properties of dust is influencing. The physical, chemical, what do I mean? I mean here composition of the dust, what elements are there. And this elemental composition of dust, it depends on geographic location. In India, it's one composition. In Sahara, in Arabic countries, different one. In Europe, different one. So also, if the solar installations is closer to some fabrics, that can be different as well. So in each and every case, it makes sense to study physical, chemical properties of dust. And not only dust composition, but also dust particle size is important issue. In some places, dust particle size can be micrometer size. In some other places, it can be nanometer scale. And if it's too small, like less than 100 nanometer, then it makes sense to study dust particle size dependence as a function of pH. And whether these particles can be further melted by water. If so, then it can go even below maybe 100 nanometer after some time, and that will be very critical for texturization of the surface of the glass. It means for certain regions, maybe texturization will not be useful. And for that reason, before mounting solar modules, it makes sense to do that study. So then zinc oxide, so next question is zinc oxide is into solar cell research for a decade. Could you tell us the role of Zinco in present day solar cell? You mentioned it as buffer layer. What is purpose? So zinc oxide, it's used as a transparent conducting material also. When it's aluminum doped, or gallium doped, it can be transparent and conducting film, and as such it can be used in many types of solar cells, in thin film solar cell technologies especially, as a transparent electrode. Yes, in antimony selenite there has been attempt to use zinc oxide as buffer layer because cadmium sulfide has been used in the first experiments, and when zinc oxide has been used, then higher efficiency has been obtained. And that result, in fact, indicated that interface between antimony selenide and then the window layer and the transparent electrode, it strongly depends on interface. So, but now, except zinc oxide, other materials are used, and iron oxide may be a good candidate for using buffer layer in antimony selenide solar cells. Very interesting questions. Thanks a lot.
If anybody have questions, they can ask directly to the speaker.
Dr. Jayama, am I audible?
Yes, yes, you are audible.
Sir, regarding the life of solar modules, will it be able to last for 20 to 25 years in the current composition we have right now in the market?
I didn't get the question. Can you please repeat?
What could be the lifetime?
Yes. Lifetime of the silicon solar cells is about 25 years. So, but it can work even longer as well.
25 years.
Yes.
Sir, will it make any difference when a solar cell is connected to a load for 25 years and the solar cell is not connected to a load?
Yes, this is a very interesting question, very important question. And the grid connected, it would be good, but then one needs conversion of direct current to alternating current, and so one needs some specific setups for that, which is giving some added cost to the PV energy. But autonomous ones are also okay to use. So,
any other questions?
yes.
You don't have any other questions? Let us conclude. I think Dr. Ajims is here. Ajim, sir?
Dr. Jairam, it's really good if we maybe include feedback link. It would be to me also very, very interesting to have feedback, and that feedback would be very useful for further updates of the lecture. And in particular, I did not hear discuss some of the very emerging solar cell concepts also, like tandem cells, for example, multi-junction cells. Just the time is limited. Yes, and just it's interesting to know which part the community would like to see, to listen to. Yeah.
Yes.
And
So I will
also
ask my
these participants are welcome to send feedback by email to me also.
Yes. I will ask my technical team to collect the feedback form.
Yeah. Thank you.
If there are no other questions, I think we can wind up. I think Dr. Ajims has left the meeting. Okay, let us conclude. The talk was very informative, very comprehensive, and thank you very much for the session. And yes, regarding the future research also, I think the MES Panani College and IFE can collaborate in future also. And I sincerely thank you for the lecture.
Yeah.
Thank you very much.
So thank you, Jairam, for inviting me. And I'm very happy to see that Dr. Nusrat Konala, she's also here in the lecture. So hello, Nusrat.
Yes.
Thank you. Yeah. So okay, then thanks a lot. So for inviting me, and good luck to all of you. Yeah. Bye bye.
Yes. Thank you. Thank you very much.